Welcome back to AP Precalculus. Today's lesson is 1.6, Polynomial Functions and Their End Behavior. All right, guys, hopefully this is a little bit of a review of last year. Hopefully you remember this. But we talked about end behavior last year, and what we're talking about is how is the graph behaving, or how does it behave as it moves infinitely left and right. So as the graph gets to positive infinity, what is it doing? As graph gets to negative infinity, what is it doing? Basically, we're trying to tell somebody what are the arrows doing? Where are they pointed, right? So in other words, end behavior is what happens to the values of your function, f of x, we could call that y if we want to, as x increases or decreases without bound. We're going to use that phrase a lot this year, without bound. That means we just keep going. We keep getting bigger and bigger. We keep going towards closer and closer to the infinities, okay? So down here, you'll see something new. This right here is called limit notation, and we are going to get very familiar with this. We do this a lot this year, okay? So if I wanted to read this has words that go with it. We would say the limit as x approaches negative infinity of f of x, right? Limit as x approaches negative infinity of f of x. You could say something along those lines, like as x values decrease without bound, the y values will do this. Okay, that's the verbal way to say it, but this is the notation way. We could do the same thing over there with the right end behavior. All right, so this little chart down here should be very familiar to you from last year. Okay, let me pull it in a little bit. You might have some of it cut off. So let's look at it like that. So we have four different possibilities for polynomial graphs. And I make that distinction because if we're dealing with rational functions, it could be a little bit different. But if it's a polynomial, meaning we don't have any x's in the denominator, it's going to be one of these four, at least as far as the arrows go. Obviously, you'd notice that there's stuff missing in the middle. That's because it could do a whole bunch of weird things in there. But as far as the arrows, they could both point up or they could both point down. The left side could be pointing down, the right side could be pointing up, or the left side could be going up and the right side going down. So what tells us if they're going in the same direction? Well, to go in the same direction, they have to have an even degree. That's why both of these are under the even degree, meaning the other ones would have to be odd degree. Well, how do I know if they go up or down? Well, the leading coefficient, the very first term, if it's written correctly, meaning that your biggest exponent is first in your polynomial, then that number in front is called the leading coefficient. If the leading coefficient is positive, it goes up. If it's negative, it goes down. That's easy for even degree. For odd degree, remember, we read left to right. So if you start at the bottom left and go up to the right, that is a positive slope, if you want to think about slope that way. So that's how you, a little bit of review from last year. Hopefully you remember that. All right, let's give example one a try. We're going to start with the behavior, and we're going to talk verbally about going to the left. So as my x decreases without bound, the value of my function is approaching positive infinity. You could say as x approaches negative infinity, y approaches positive infinity. Okay? Let's try it with our limit statement now. So we're going to do limit as x approaches, and we're going to go to negative infinity, right? What does our function do? Well, it goes to positive infinity. How about the right-hand behavior? Verbally, as x grows without bound, our y values go to negative infinity. They decrease without bound. As my x numbers get bigger, my y values get smaller. What's our limit statement look like? The limit as x approaches positive infinity, f of x becomes negative infinity. All right, guys, let's go ahead and pause the video, and I want you to give this one a shot. You could write out the behavior verbally if you want to. I'm not going to. I'll say what it is verbally, but go ahead and give it all a try. All right. So verbally, I would say as x approaches negative infinity, y approaches positive infinity. That's how I'd write the left behavior, or say the left behavior. My limit statement, as x approaches negative infinity, f of x approaches positive infinity. All right, for right behavior, verbally, as my x approaches positive infinity, my y approaches positive infinity. How about that limit statement? My limit, as x approaches positive infinity, y approaches positive infinity. And there we have it. All right, here in example 2, they want us to graph a possible polynomial function. Now remember, it's got to be a function, so you can't backtrack on itself. And polynomial means it has to be smooth curves. There can be no points. There can be no jumps, no skips, or anything like that. All right, so what's going on here? As I go to negative infinity, my y has to go to negative infinity. So as I go this way, my y's got to go this way. So at some point, I got to be down here, right? And then as my y goes to positive infinity, I'm still going to negative infinity. So I got to be down here somewhere. Okay, so as long as you hit here and here, it can do whatever it wants in here. You could have it go crazy as long as you're not going back on itself. Looks like a great graph. How about B? Let's take a look. As I go to negative infinity on my x-axis, my y-axis is going to negative infinity again. That tells me I'm down here somewhere. And then as I go to positive infinity, y goes to positive infinity, so I'm up here, right? So as long as I have this down here and this up here, it could do whatever it wants in the middle. Woo, I'll give it a little extra. And just remember, they did not give us near enough information to get a real graph. These are just possible graphs that could, as long as they meet what they gave us, we're okay. Okay, for polynomial equations, it's easiest to find the end behavior of the right side first, meaning that we're going to move from left to right. We're used to that. So if we go up, that means I have to have a positive leading coefficient. If I go down, I have to have a negative leading coefficient. Okay, and then after you get that side, for the left side, you want to look at the degree. Okay, if the degree is positive, they're going to go in the same direction. Okay, so same direction, the degree would have to be even. Yes. If they're going in opposite, too many letters, I'm just going to go OPP, direction. That has to be an odd degree, okay? Maybe a way you can remember opposite direction is OPP looks really close to ODD, like the P's got flipped upside down, and you would get odd. So let's look at these examples down here. A, x to the fifth. I don't really even care. Well, I do care about the 4, but x to the fifth, I know that it's got to look like that because it's odd. They have to go in opposite directions. And since 4 is positive, then we know that it has to go uphill. So we're going to use our infinity signs. The left is going to be negative infinity, and the right is going to be positive infinity. What about the next one? Well, I know they're going in the same direction because it's even exponent, and it's a positive coefficient, so it has to look like that. So we have positive infinity and positive infinity. Okay? All right, C. We have a 6 as our exponent. That means they're going in the same direction. Our coefficient is this guy out in front, -2. So they have to be going down like this. So they're both negative infinities. Let's move this up a little bit so we can see a little bit. All right. Now, they didn't write this next one in a great order. If you wanted to, you could rewrite this as negative x to the fifth plus 3, but you don't have to. You can look at the biggest exponent and go, oh, that's negative, and it's got an odd, so it has to be going downhill, so it's like this. So we got positive and negative. Same thing with E. They hid that guy way back there. It's the exact same thing as the last one, so same answers here. Now, the last one's a little bit tricky because this is one term. They did not FOIL it out. And we don't need to FOIL it all out. That'd be a little bit of extra work. We just need to multiply all the x's together. And that's going to give us negative 2x to the third. And then just like the last couple, it looks like that. So we got positive infinity to negative infinity. All right, let's go ahead and write some limit statements for the end behavior of our two functions here. So I'm going to start out with limit as x goes to positive infinity. Do the right first of our f of x. All right, so let's look at this. We have an even degree, which means they have to go in the same direction, both up or both down. And our coefficient is negative, so I know that they're going both down. So f of x will be approaching negative infinity. So when I do the other side, to the as x approaches negative infinity, it will be doing the same thing. Go ahead and pause the video and give b a shot. All right, so here we go. Limit as x approaches positive infinity, g of x. All right, let's see what we got here. We got an odd function, so they got to go in opposite directions. And we have a positive coefficient, so we got to be going uphill. So it has to look something like that. So my g of x from that side will be going to positive infinity. And when we flip it around and go to negative infinity, we'll be going in the opposite direction, which will be negative infinity. All right, our last example here wants us to use our graphing calculator to determine the end behavior. So really, we're just going to look at the graph. All right, so take a second and graph these guys, and then we'll get going. So here's our first graph. So if I want to do my limit statements, limit as x approaches positive infinity, I'm moving right on the graph. So I'm going this way. My f of x is also approaching positive infinity. And what happens on the other side is it also approaches positive infinity. All right, there's b. So now when we're talking about going to positive infinity, oh, wait, what is going on there? I'm not going towards infinity. Where am I? Kind of leveling out, aren't I? Where am I leveling out at? If you kind of pull into that, you can see that it looks like we're leveling out at around 2, right? What about the other side as I go to negative infinity? What's going on there? The same idea, right? I'm leveling out at 2. Well, when your positive and negative domain infinities are going to the same thing, that's the definition of a horizontal asymptote. And you should remember a little bit about horizontal asymptotes from last year. Okay, let's look at the last one. All right, here we are. It's a weird looking graph, but we're just talking about the end behavior. So limit of h of x as x approaches positive infinity. That looks like it's leveling out at 0, and the same thing from the other side. Looks like it's approaching 0. We'll have more on horizontal asymptotes coming up, but that's a little foreshadowing for you.